Well, welcome back to Lesson 13 in our study of the transport layer of the TCP/IP model. Now, you'll recall that this is the layer that is responsible for end-to-end communication. That is, it is responsible for ensuring that the message that is sent is the message that is received at the other end. Now, we've already talked about the two main protocols of the transport layer, TCP and UDP, and the differences between the two. We've also discussed the issue of error detection and correction as the string of bits is transferred from one host to another. Now we're going to discuss another issue, the issue of flow control. We have to recognize that as all these bits are being transferred from one end of a network to the other end of a network, that there are different kinds of equipment operating in different kinds of environments from one end to the other. And their capabilities may not be the same. The burden in terms of what they're trying to process may not be the same. And it's very possible that the receiving host could be overwhelmed with bits and as a result not be able to process them and just end up dropping them. Recall that the host on each side of the TCP/IP connection set aside a receive buffer for the connection. When the TCP connection receives bytes that are correct and in sequence, it places the data in the receive buffer. The associated application process will read data from this buffer, but not necessarily as soon as the data arrives. The receiving application may be busy with some other task and may not even attempt to read the data until long after it has arrived. If the application is relatively slow at reading the data, the sender can very easily overflow the connection's receive buffer by sending too much data too quickly. TCP provides a flow control service to its applications to eliminate the possibility of the sender overflowing the receiver's buffer. Flow control is a speed matching service, matching the rate at which the sender is sending against the rate at which the receiving application is reading. A TCP sender can also be throttled due to congestion within the IP network. This form of sender control is referred to as congestion control. Even though the actions taken by flow and congestion control are similar, they are taken for very different reasons. So now let's discuss how TCP provides its flow control service. Throughout this lesson, let's assume that the TCP implementation is such that the TCP receiver discards out-of-order segments. TCP provides flow control by having the sender maintain a receive window variable, RWND, which is advertised to the other side of the communication. Informally, the receive window is used to give the sender an idea of how much free buffer space is available at the receiver. Because TCP is full duplex, the sender at each side of the connection maintains its own receive window. Suppose that host A is sending a large file to host B over a TCP connection. Host B allocates a receive buffer to this connection. From time to time, the application process in host B reads from the buffer. The receive window capacity will fluctuate as data is taken from the application and more data is received from the sender. Depending upon the available capacity, the receiver may or may not accept data from the other end. As the application process at host B empties the buffer, TCP does not send new segments with new values for the variable for the window capacity to host A. TCP sends a segment to host A only if it has data to send or if it has an acknowledgement to send. Therefore, host A is never informed that some space has opened up in the host B's receive buffer. Host A is blocked and can transmit no more data. To solve this problem, TCP specification requires host A to continue to send segments with 1 byte of data when B's receive window is 0. These segments will be acknowledged by the receiver. Eventually, the buffer will begin to empty, and B's acknowledgement will contain a non-zero value, allowing host A to send more. In this lesson, we take a closer look at how a TCP connection is established and torn down. This issue is important because TCP connection establishment can significantly add to perceived delays. Furthermore, many of the most common network attacks exploit vulnerabilities in TCP connection management. Let's examine how a TCP connection is established. Suppose a process running in one host, the client, wants to initiate a connection with another process in another host, the server. The client application process first informs the client TCP that it wants to establish a connection to a process in the server. In other words, the top layer informs the layer below it, the transport layer, that it needs a connection. The TCP in the client then proceeds to establish a TCP connection with the TCP in the server in the following manner. Step 1. The client-side TCP first sends a special TCP segment to the server-side TCP. The special segment contains no application layer data, but one of the flag bits in the segment's header, the send bit, is set to 1. For this reason, this special segment is referred to as a send segment, SYN. In addition, the client randomly chooses an initial sequence number, client ISN, and puts this number in the sequence number field of the initial TCP send segment. That's SYN. This segment is encapsulated within an IP datagram and sent to the server. There has been considerable interest in properly randomizing the choice of the sequence number in order to avoid certain security attacks. Step 2. Once the IP datagram containing the TCP send segment arrives at the server host, the server extracts the TCP send segment from the datagram, allocates the TCP buffers and variables to the connection, and sends a connection-granted segment to this TCP client. This connection-granted segment also contains no application layer data. However, it does contain 3 important pieces of information in the segment header. First, the send bit is set to 1. Second, the acknowledgement field of the TCP segment header is set to client underscore ISN plus 1. Finally, the server chooses its own initial sequence number, server ISN, and puts this value in the sequence number field of the TCP segment header. This connection-granted segment is saying, in effect, I received your send packet to start a connection with your initial sequence number, client ISN. I agree to establish this connection. My own initial sequence number is server ISN. The connection-granted segment is referred to as a SYNAC segment, SYN acknowledgement, SYNAC segment. Step 3. Upon receiving the SYN acknowledgement segment, the client also allocates buffers and variables to the connection. The client host then sends the server yet another segment. This last segment acknowledges the server's connection-granted segment. The client does so by putting the value server underscore ISN plus 1 in the acknowledgement field of the TCP segment header. The SYN bit is set to 0 since the connection is established. The third stage of the three-way handshake may carry client-to-server data in the segment payload. Once these three steps have been completed, the client and the server host can send segments containing data to each other. In each of these future segments, the SYN bit will be set to 0. Note that in order to establish the connection, 3 packets are sent between the two hosts, as illustrated in the figure that you see here. For this lesson, this connection establishment procedure is often referred to as a three-way handshake. At some point, the TCP connection will end. Either of the two processes participating in the TCP connection can end the connection. When a connection ends, the resources, that is the buffers and variables, in the host are deallocated. As an example, suppose the client decides to close the connection. The client application process issues a close command. This causes the client TCP to send a special TCP segment to the server process. This special segment has a flag bit in the segment's header, the FIN bit, set to 1. When the server receives this segment, it sends the client an acknowledgement segment in return. The server then sends its own shutdown segment, which has the FIN bit set to 1. Finally, the client acknowledges the server's shutdown segment. At this point, all resources of the two hosts are now deallocated. Why don't we conclude this lesson here? Take a few minutes to review what we've covered. Take care of any assignments that you may have. And when you're ready, come on back and we'll continue our discussion.